For pages 4 and 5 of the scheduling notes, we're going to look at a RTOS2 code example, and it implements the program described on the previous page. Before we get there, just one thing. I said that task 1 is normal priority and task 2 is low priority. I didn't explain what that meant. We're using a fixed priority scheduler, and what it will do is whatever task that's ready that has the highest priority, that's the one that it runs. So that would mean that if you had a high priority task that never stopped or didn't block, then your low priority task would never get to execute. Your task will block periodically, and we'll see that in this example I'm going to show you. So I'm at the Learn site. Let's go to Lectures and then to Handouts. Then it's the RTOS2 demo, and I'm going to download that. And so this will be page 4, and this will be page 5. I'm going to start at the top of this page first. So you can see that there are 4 header files, and standard bool and standard IO you should know by now. Simsys OS2, that's the first time we've encountered in lecture. So this is the RTOS header file. I'll just say RTOS header. LPC17XX, that is for our microcontroller unit, so it defines the peripherals and stuff like that. So the MCU header. So you're always going to need to include both of those for any code that runs on this processor with this OS. And there is one global variable here. It is an operating system object called an event flag, and it's used to communicate between threads and also between ISRs and threads. So this is our first example of inter-process communication, it's usually called, or in this case inter-task communication. So we don't know what's inside this type. It's OS event flags ID type. It's probably a struct, but it doesn't matter. We just use OS functions to interact with it. Now those functions require us to select which it's a 32-bit flag. So this is a 32-bit flag, and we need to tell it which bits we're interested in, and that's what this macro up here is for. So the macro, it's in hexadecimal, that's 8 hex digits or 32 bits. The UL at the end of it says that it is an unsigned long integer literal. And so here bit 0 is set in this flag. So we're going to be using bit 0 of the event flags, and the other 31 bits we're going to leave alone. Okay, so now let's go down to main. And so main, just right from the start, it defines the period for task 2, how long between flashes of the LED. It's going to be turning the LED on and off at a rate of once a second. So it'll be on half a second, off half a second. Next thing we do is we initialize the OS kernel. This, as far as I know, sets up data structures for tracking tasks and stuff like that. The documentation really doesn't say much about what it does, but you need to do this step before you create any OS resources like threads or event flags. So next we have 3 lines of setup code. So setup LEDs, that's going to make all the LED pins outputs in the general purpose IO. So I'm going to go to that function right now. So we have, let's just draw a line here to separate these. We have 8 LEDs, and they're located on GPI port 1, pins 31, 29, and 28. You'll notice that pin 30 was skipped for some reason. That would have been the system designer that chose that. And then the other 5 LEDs are on GPIO port 2 and they are bits 6, 5, 4, 3, and 2. So let's just look at these two lines. GPIO1 is for port 1, and we're setting the fast I/O direction. And so wherever we see a 1 in this constant on the right, we're going to be turning that bit on, making it an output. So if you take this B000, etc., and write it out as a 32-bit value, you'll notice that bit 31, the most significant bit, is a 1, bit 29 is a 1, and bit 28 is a 1. So that corresponds to those three pins, or the three LEDs. And then we've got port 2, and they're all 0 except for some bits here. So the pattern that 7C makes in binary is that 7, and C is 12, which is 8400, 12 in binary. And so this is bit 0, bit 1, those are both off, but then you see bits 2, 3, 4, 5, and 6 all have 1, so they're all outputs. We make these into outputs, and those are wired to the LEDs. So now by writing to the LED data registers, which T2 will do, we can set the bit to 1 or 0 to turn the LED on or off. Okay, back to main. So next thing we do is we initialize our event flags object. So all of our operating system calls, you might have noticed by now, start with an OS. And if you're creating a new object, then it'll end with new. And usually when you're creating an operating system object, you can pass it a pointer to an attribute structure which defines the parameters for that object. So here, by passing in null, we are accepting the default attributes for event flags. And then we set up the push button, and this is going to look kind of like what we saw in the I/O push button example. So let's go up to that function. So here we are at the setup push button, and so we enable the push button to interrupt the processor on the falling edge of this is going to be pin 10, and that's the push button. So when we see the push button go from a 1 to a 1 to a 0. So normally when it's not pushed, it's a 1. When it's pushed, it's a 0. So when it goes from 1 to 0, we're going to the port will interrupt the processor, and then the next line is to allow the interrupt request at the processor. If you don't do this step, then it just by default ignores IRQs. So it's telling the interrupt controller to accept those interrupts. When those interrupts come, it's going to run the handler right here. So there's our push button ISR, and it's the first line is the same as in the previous example. So we're going to clear the interrupt on pin 10. So when that button's been pushed, we're going to say, okay, we got the message. You can drop your interrupt request. And then the other thing that it does is it sets an event flag. So we give it the event flags variable that we had initialized before, and we need to tell it which bits in that flag to set. And so that's what this macro is for that we looked at above. So we're going to set bit 0 to 1. Now back to main. The order here, this order matters. The reason is that once we've enabled interrupts, the interrupt service routine can run as soon as we press that push button, and it's going to try to set the event flag bit. And so if we hadn't initialized the event flags first, then that's an uninitialized object, and who knows what calling that OS event flag set function would do. It would give you erroneous or undefined behavior. So that's why that matters. And we're going to create two more, I guess you could call them objects or operating system resources before we start the kernel running. And so we're going to create two threads. So RTOS2 calls tasks threads. The term thread comes from multiprocessing operating systems. RTOS2 isn't really that kind of model, but they borrowed that term. So I say tasks, they say threads. So tomato, tomato. So first we give it the function pointer. So that's what function that thread is going to run. We'll look at that in a second. Then we pass it a parameter, in this case null. It's not going to use the parameter. And then the next null is for the attributes. So there's two threads we're creating. So I'll annotate the second one. So the second parameter there is the function argument. And then here again, these are the attributes for the thread, and we're accepting the defaults by passing in a null pointer there. So now let's go look at thread 1. So we created these threads, they're not running yet. So thread 1, it tells you at the top, it waits for the button push and then it prints a message. And so let's look at it. We've got an infinite loop here, and here is our wait. So it's going to wait for an event flag to be set. So we need to pass it the event flags variable. We need to tell it which bits we're interested in, so we use that macro for that. And we're only interested in bit number 0. That's all we're using in this example. And this parameter here, you can choose to wait for all of the bits to be set or any of them to be set. In this case it wouldn't matter because there's only one that we're specifying, but it can be OS flags wait all as well. And then the last parameter is how long to wait for that to happen. If it doesn't happen, should it time out? Here we say OS wait forever, and we're going to see that that's what we use in almost all of our examples. So that just says wait until that event flag is set by the ISR. Don't just wake up. Now you can specify, this is a timeout value that you can specify, and it's in operating system ticks, and the OS tick is defined by default to be 1 millisecond. So every 1 millisecond the system tick timer is generating a tick. It's actually generating an interrupt request, which causes that sysTick handler to run. Right. We could also have used the timeout of 0, and then this would return right away if that flag was, whether or not that flag was set, and then you'd have to look at the return value to see what happened. So you'll notice that I'm not examining the return values from these OS calls. If this was production code, you would definitely need to do that. Remember the power of 10 rules, that was one of them, but it would just clutter this example too much. So we wait, and while the flag is not set, so when we haven't pressed the button and the ISR hasn't run, the flag is not set, T1 is blocked here, so it's not actually running. It's in the block state, and the scheduler is going to ignore it. It's not going to run it until it's ready to run. Once the ISR runs, it sets that flag. That communicates that thread 1 should now be woken up and it can run. And when that happens, it's going to print to the UART button pushed. So I ran this in the simulator today, and it worked. So that's always nice. Task 2, its job is to flash an LED, just to show you two things running at the same time. And so the first thing that it does is it looks at its argument. So the thread parameters are always void pointer. It's kind of like a generic or a template variable, sort of. It's as close as you get in C. So you pass in a void pointer, and then you cast it to whatever you know the parameter is, and you can dereference it. In this case, I knew that we passed in a pointer to the T2 period, so I can dereference that as a uint32, and I'll get the value 1 in this case. the next step is I'm setting the priority to low, just for this example. So that means that thread 1 and thread 2 are both ready to run. Thread 1 is going to be the one that gets to run. Thread 2 has to wait until thread 1 is not able to run before it gets to run. Again, we have an infinite loop, and this line here is going to turn pin 6 of port 2 on. So that's going to be setting on the board, I think it's the leftmost LED on, and then we have a delay here. So OS kernel get tick frequency, that's going to return 1,000. There's a tick 1,000 times a second, and so it's going to delay for 1,000 ticks times the period, which was 1, divided by 2, so half the period. So like it says here, the LED is on for half a period, and then it's going to be off for half a period. So when we are on this line here, the OS delay, task 2 is now going to be blocked as well. So maybe neither task 1 nor task 2 is ready to run. And then there's an idle thread. I keep mixing task and thread. But thread 1, thread 2 can't run, then an idle thread will run. Once that delay ends, task 2 is ready to run, and it is going to clear pin 6. It's going to turn it off, and then it will delay again for half the period that was defined in the argument. So that's task 2. And so once we've created those 2 threads, we've done all that other setup, the last thing that we do is we do kernel start. So this starts the scheduler, and this call should not run. So that for loop that's before there is only for debugging. If OS kernel start fails for some reason, you'll get to that for loop, and in the debugger you can examine variables and things to try and figure out why OS kernel start might have failed. We're not going to see that in this course, or at least I hope you aren't.